Welcome to Edu Explorers, Journey into Knowledge. Understanding resistance. Resistance is slowed down or opposes the flow of electric current. The SI unit of resistance is the ohm, represented by the Greek letter omega. Resistance measures how much a conductor opposes the flow of electric current. If the potential difference voltage across a conductor is 1 volt and the current passing through it is 1 ampere, then the resistance R of that conductor is 1 ohm. Mathematically, this is expressed as 1 ohm is equal to 1 volt by 1 ampere. Resistance and current have an inverse relationship. As resistance increases, the current through the conductor decreases. For example, if the resistance doubles, the current is reduced by half. To demonstrate, let's conduct an experiment with a broken circuit, closing it with different types of materials and measuring the current flow using an ammeter. Close the circuit with wire A. Note the current readings on the ammeter. Replace wire A with wire B. In this case, the ammeter shows a lower current than wire A. Replace wire B with wire C. Here, the current is even lower than wire B. Replace wire C with wire D. No current passes through and the ammeter shows no reading. From this experiment, we observe that wire A allows the most current to pass and therefore act as a good conductor. Conductors, resistors and insulators. A good conductor is a material with low resistance that allows electric current to flow through it easily. Wire B in our example acts as a resistor, which is a material with some resistance but still allows current to flow. Wire C is a poor conductor, which means it has a higher resistance and allows less current to pass through. Lastly, wire D is an insulator, a material with very high resistance that makes it extremely difficult for electricity to flow through. Factors affecting resistance. The resistance of a conductor depends on several key factors. Length of the conductor. Resistance increases as the length of the conductor increases. Cross-sectional area. Resistance decreases as the cross-sectional area of the conductor increases. Nature of the material. Different materials have different resistance based on their atomic structure. Mathematically, resistance is directly proportional to the conductor's length and inversely proportional to its cross-sectional area. The formula incorporating these factors is R is equal to rho L by A, where R is the resistance, L is the length of the conductor, A is the cross-sectional area, and rho is the resistivity of the material. Resistivity and material properties. Resistivity is a unique property of each material. Metals and alloys. These typically have low resistivity, making them good conductors. For instance, copper and aluminium are widely used for transmission lines because of their excellent conductivity. Tungsten has a higher melting point, making it ideal for filaments in light bulbs. Alloys. Although they have higher resistivity than pure metals, alloys are used in electrical devices because they are oxidation resistant at higher temperatures. This property makes them suitable for heating elements in devices like electric irons and toasters. Insulating materials. Materials like rubber and glass have very high resistivity, ranging from 10 to the power of 12 ohm meter to 10 to the power of 18 ohm meter, which makes them excellent insulators. Both the resistance and resistivity of a material can change with temperature. Resistors in series and parallel. In complex circuit, multiple resistors are often used in either series or parallel arrangements. Let's explore the difference between these two types of connections. Connection type, series. Resistors are connected end to end in a single path. This creates only one path for the current to flow through all resistors sequentially. The current flowing through each resistor is the same as there's only one path. Connection type, parallel. Parallel. Resistors are connected across the same 2 points, creating multiple paths for the current to flow simultaneously through each resistor. The current divides among the parallel branches. The current through each branch depends on the resistance of that branch. Lower resistance path will carry more current and higher resistance path will carry less. Each arrangement affects the overall resistance and behavior of the circuit differently, which can be useful for achieving desired current and voltage characteristics. Voltage distribution. In series, the total voltage across resistors in series is the sum of the individual voltage drops across each resistor. Each resistor experiences a different voltage drop based on its resistance. Parallel. All resistors in a parallel circuit have the same voltage across them, equal to the voltage of the entire parallel network. Total resistance. Series. The total resistance in a series circuit is the sum of all individual resistance. Rs is equal to R1 plus R2 plus R3 plus so on. As more resistors are added in series, the total resistance increases. Parallel. The reciprocal of the total resistance in a parallel circuit is the sum of the reciprocals of each individual resistance. 1 by R, adding more resistance in parallel decreases the total resistance. These properties are essential for managing voltage and resistance in complex circuit to control current and power distribution effectively. Effect of circuit and heating effect of electric current. Effect on circuit. Series circuits. Increasing resistance by adding more resistor in series reduces the current in the circuit for a given voltage. This is because the total resistance increases, limiting the current flow. Parallel circuits. Adding more resistor in parallel decreases the total resistance, which increases the current in the circuit for the same voltage. Heating effect of electric current. When electric current flows through a conductor, it encounters resistance. These resistance convert some of the electrical energy into heat energy, a phenomenon known as the heating effect of electric current. For example, a fan running for a long period will heat up due to this effect. Certain devices such as electric irons are designed with materials that have higher resistance to initially produce heat, which is used for their function. This heating effect is useful in devices designed to generate heat but can also be an indicator of energy loss in other circuits. Joule's law of heating. Joule's law of heating describes how electrical energy is converted into heat energy when current flows through a conductor. This principle is a key to understanding the heating effect of electric current and is used in devices like heaters, irons, and filament bulbs. According to Joule's law, the heat generated in a conductor is directly proportional to the square of the current I square passing through the conductor, the resistance R of the conductor, the timing t for which the current flows. Mathematically, Joule's law is represented as H is equal to I square RT. This means if the current through the conductor increases, more heat is generated due to an increase in the number of electron-atom collisions within the conductor. Higher resistance. When the conductor resistance is high, it resists the current more strongly, resulting in greater heat production. Longer duration. The longer the current flows, the more heat is accumulated over time. In practical applications, this law explains why devices with higher resistance or prolonged current flow generate significant heat. Applications of Joule's law of heating. Electrical heaters. Joule's law is applied in electrical heaters, where electrical energy is converted into heat to warm a room. The heating element with high resistance generates substantial heat as current flows through it. Electric irons. In electric irons, the heat generated by the current is used to press cloths. The heating element inside the iron with controlled resistance provides the necessary temperature for ironing. Fuses. Fuses are safety devices in electrical circuits. They are designed to melt and break the circuit if the current exceeds a safe limit, protecting the circuit from damage. The melting occurs due to the heating effect of electric current as described by Joule's law. In summary of this part, resistance in conductors arises from the attraction between electrons and atoms, slow down electron movement and thus opposing current flow. Materials differ in resistance. Good conductors allow easy current flow, while poor conductors allow less. Insulators with very high resistance block current. Resistance depends on a conductor's length, cross-sectional area, and material type. Such circuits add resistance, while parallel circuits reduce it. Joule's law explains the heating effect of resistance where electrical energy transforms into heat applied in devices like heaters, irons, and fuses to prevent circuit damage. Thank you for watching. If you find this video helpful, please like, share, and subscribe to our Edu Explorers.